Hey, this is Mr. Weisfeld. We're finishing off the AP summer assignment, AP Physics. This is part 2 video. Part 1 video was done a while ago, so let's pick it up where we left off. We left off with problem number 53, so check this out here. You have an equation F1 plus F2 equals Ft, and F1 D1 equals F2 times D2. Solve for F1. So in the end, I want an equation that has F1 on one side, and then I want some function. We use this sum function that only has Ft, D1, and D2. So it's okay if you don't understand this notation right here, but this helps me remind myself that I don't want to see an F2 in my final equation. I only want to see an Ft, a D1, and a D2. So let's get started here. So if I have, you can start with either equation, but let's get it just set down so that you know which one you're going to start with. So F1 equals Ft minus F2. And then we check, we say, does this meet the requirements? No, not quite yet. I have to basically get rid of the F2. So if I have F2, I can write an equation for F2 from this equation. So F2 equals F1 times D1 divided by D2. So here's the thing. This equation here came from this equation right here. Just rearranged. I divided both sides by D2. I suppose I could be really hyper kind of specific about that. And this equation here came from that first equation. And what I notice is F2, I can put it in over here. And so now if I take this equation and put it, see this F2 right here? I'm going to put it in for that F2 right there. So I'm going to get F1 equals Ft minus F1 times D1 all over D2. And then what you see is that you've got an F1 in a couple of places. In order to solve, your equation needs to have F1, only F1 on one side, and the other side some combination of Ft, D1, and D2. So how about this? Let's do this. Add this term to both sides. So I have F1 plus F1 D1 all over D2 equals Ft. Good, but now what I can do is I can factor out an F1 over here. So so you can do these big equal signs to say there's like a whole equation on either side of the big equal sign or the arrow. So then I'm going to get over here, color that in. I'm going to have F1 all by itself. I had F1 times 1 plus D1 over D2. So this equals Ft all over 1 plus D1 all over D2. So that's your answer right there. You can double check. Let's see, if D1 equals 0, then F1 equals Ft. So if D1 equals 0, F2 equals 0, F1 equals Ft. So that's just a quick check. If I said that Ft equals 1 plus D1 over D2, not quite obvious that I can make F1 equals 1. But you can go back and double check these equations here. So that was question number 53. Here's question number 54. Again, I want to solve for R in terms of Fc, M, and V. So one way to do this is to ask yourself what is missing in the final equation. So there's no AC in the final equation. So when you have one equation with that variable already solved for, just plug it in. Take this AC and plug it in right here. So if you'll allow me, Fc equals m times AC, but m times AC equals m times v squared over r, right? Because I plugged in this AC here. This is the AC. And then we're solving for r, so r equals, multiply both sides by r, divide both sides by fc, m v squared all over fc. So that's our answer for question 54. Let's do question 55. You can double check your answers. If t equals 2 pi times the square root of L over G, and t equals 1 over f, solve for L in terms of pi, G, and f. So what's the variable that we don't have in the end is there's no t in the end. And these equations both have t solved for, so this one should be relatively easy. 1 over f, that's t equals 2 pi times the square root of L over G. So once again, this whole equation here was t, and this whole equation here, or this expression here, was t. So I just, I think that's a transitive property of equality or something. If A equals B and B equals C, then A equals C. Anyway, so now we have to solve this equation for L. So L is under the square root. You have to square both sides. So 1 squared over f squared equals 4, 2 squared, pi squared, L over G. And if you get L all by itself, you basically have to do G on top, multiply both sides by G. 4 pi squared f squared equals L. So I basically took the G up and take the 4 pi squared down. Divide both sides by 4 pi squared. Alright, so that was number 55. Here we go to, I want to go to page 10. Okay, moving on. Question number 56. If a line r equals c minus x star t was graphed on an r versus t graph, what would the following be? So we know that y equals mx plus b. That's the standard format. And so whatever is here when you say r versus t, this must be like y versus x. We always say it that way, in that order. That must mean that y is like r. So this here is like y. And this here, the t, must be like x. So we're not going to be confused that this is called x star. Whatever's in front of the x is x star. So is m, is the slope. So remember, m is the slope. And so the slope in this case is minus x star. Wow, that's really ugly. Let me erase that and write it a little bit better. I could probably zoom in a little bit here. So the slope is minus x star, asterisk, whatever. And the y-intercept, whatever is hanging alone by itself out here and isn't mentioned in y versus x, must be b. So that that in this case must be the c. So y-intercept must be c. So this comes from knowing, first of all, the equation for a line, and then how we talk about graphs of lines. All right. Sketch the relationships given. Question number 57. So on the y versus x graphs below, sketch the relationships given. Y equals mx plus b. That's the standard format. This is the slope right here, m. And b is the intercept. So if the slope is greater than 0, m is greater than 0. That's another way of saying that. And if b equals 0, the y-intercept equals 0, all these lines have to go through here, the point y equals 0. So they all have the point y equals 0. That's it's going to be true for all of these lines. But remember, there's a bunch of lines that go through that point, and they all have different slopes. So do they have slope like this? That's actually m is less than 0, so that's not the one. Do they look like this? That's the slope equals 0. So they all have slopes that go upwards as you go from left to right. That's m is greater than 0. So I can draw a line here. That's a solution. I can draw another line that's greater than 0 that goes through the origin like that. I can even draw a line that's oh so close to being flat but still has some slight positive slope. Those are all lines that go through the point y equals 0. And those are all lines that have positive slope. So this is what we get for A. For B, if m is less than 0, what we said is the slopes have to go down. But if b is greater than 0, these are all lines that go through points here where y is greater than 0. So let's see if I can do a bunch of lines here. The slope goes down. So this line here is a solution. It has slope less than 0, and it has a y-intercept that's greater than 0. This line here also works. And this line here, because it's not flat, and you know, those lines could have intersected each other. They could have overlapped, but I just wanted to keep them separate here so you could see that they all have slope, negative slope. We call this negative slope. And we call this positive y-intercept, which is true for all those drawings right there. Let's take a look at the next questions here. Question C. Y equals x squared. What does y equals x squared look like? Well, you can do a table. X and y. If x equals 0, y is x squared. If x equals 1, y equals 1. If x equals 2, y equals 4, because y equals x squared. So you should see that if it equals x squared, you could write it up there even just to remind yourself. So I basically have to go through the point 0, 0. And let's say this is 1 and this is 2. So this is 1, 2, 3, 4, kind of pushing it, right, on my scale. But if x equals 2, y equals 4, and if x equals 1, y equals 1. So this graph looks like this. Now, quick question. What happens over here for x equals negative 1? Or for x equals negative 2? What do we do then? Well, x squared, the sign doesn't change, so this point here is going to be 1. Negative 1 squared is 1, and negative 2 squared is positive 4. So this parabola goes up here as well. I think I stretched that 2 out a little bit too much. So we'll take a look at maybe how to smooth this out here in just a second. So we call this a parabola that opens up. Y equals the square root of x. So here's my little table. If x equals 0, y, which equals the square root of x. So if x equals 0, y equals 0. If x equals 1, y equals 1. And if x equals 4, y equals 2. So notice I picked the numbers that help me out, right? So if x equals 0, we're at 0. We can put that point in here. And 1, 2, 3, 4. 1, 2, 3, 4. So when x equals 4, y equals 2. When x equals 1, y equals 1. So this is a parabola that's opening up here on the side. Now the question is, isn't it true that the square root of a number, we can't take the square root of negative numbers, so we're not going to have any solution over here where x is negative, but it is true that the square root of 4 is 2 or negative 2. So the answers here are also 0, negative 1, and negative 2, which means that negative 2 squared equals 4. Or the square root of 4 is plus or minus 2. The square root of 1 is 1 or negative 1, positive or negative 1, and the square root of 0 is always 0. So I can also do, let's do my scale down here, negative 1, negative 2, negative 3, negative 4. And this was 1, 2, 3, 4. So there is also a solution down here where the square root of 1, positive 1 is negative 1, and the square root of 4 is also negative 2. So this thing also opens down this way. If you've got something like that, you get full credit. Nice job. All right. Now let's do y equals 1 over x. So, you know, the funny thing, when x equals 0, this is a very big number, so we say infinity, so that's very big. But if x equals 1, y equals 1. 1, 2, 3, 4. And this is, let's see, y equals 1 over x. If x equals 2, y equals 1/2. And if x equals 4, y equals 1/4. So it's almost like you want to stretch out this graph and say this is 1/4, 1/2, 3/4, 1, and then you can do quarters this way too. But then I'm not going to be able to show x equals 4, so this is probably going to have to be equal to 4 here, and this is 1. And what you get from x equals 1, y equals 1 is that point there, and you go up pretty steep. And over here, when you get to 2, you're at 1/2, and when you get to 4, you're at 1/4. So it's a curve that, we call that a hyperbola. And it has this general shape, an inverse relationship shape. Y equals 1 over x squared. Let's make our table. If this is x, and this is y, again, x equals 0 is not really a defined point on this graph. The graph is we say it's unbounded. It grows very large. If x equals 1, y equals 1, so that point's still good. So let's do 1, 2, 3, 4. Like we did before, and 1, 2, 3, 4, and y. If x equals 2 now, here's the funny thing, y equals 0.25, which equals 1/4, right? And if y equals 4 or 3, it's like a 9th or a 16th, so super small. And so what you would do here is you would say that this graph is getting smaller much quicker than the other graph. So this one is shooting up much faster and then going down much quicker. So that's 1 and 4 and 1. So you can maybe see, hard to see on these really small graphs, but you can see maybe some difference there. And now let's do y equals 1 over the square root of 1 over x. you realize that this is also 1 over the square root of x. That's the same thing. You take the square root of the top and the bottom. So let's do this. X and y. X equals 0. Y is basically very large. X equals 1. Y equals 1. X equals 2. 2 is going to be 1 over the square root of 2. Not really easy to see what that one is. But 4 for x is y equals 1/2. So let's do these axes again. 1, 2, 3, and 4. And 1, 2, 3, 4. 1 to 4 in x. And if this is 1, then we get all the way over here at 4 before we're at 1/2. And so this one is not climbing near as quickly as the other one. So it's nice and easy. So that's the graph of y equals 1 over the square root of x. So notice that the shape of these are all basically hyperbolic or inverse relationships between y and x. So the two words hyperbola or inverse relationships. We say inverse because as x goes up, y goes down, or as y goes up, x goes down. Yeah, okay. So now y equals sine of x. Sine is called a transcendental function. It's also called a circular function. Here's what you need to remember. SOHCAHTOA. Sine is the opposite over the hypotenuse. Cosine is the adjacent over the hypotenuse in a triangle, and the tangent is the opposite over adjacent. So we have a pretty cool way of thinking about sines and cosines on the unit circle. We call it the unit circle because it has a radius of 1. If I draw my circle here, I know that this point here is 1. That's the radius. And I know this angle here I could define to be like some angle. Let's say it's x, actually. So in this case, the sine of the angle is y, but the sine is the opposite over the hypotenuse. Sine of the angle is the opposite over the hypotenuse. But in this case, the hypotenuse is always 1, so the sine of x is the opposite. Which means this length right here is the sine of that angle. So the cool thing is when the angle x is 0, so let's do our little table x and y. When x is 0, y equals 0, so that's a point right here. When x equals, I could plug in numbers, but we really like to talk about things like pi and pi over 2. So this angle right here, this is x equals pi over 2. This angle right here is x equals just pi radians, or 180 degrees. So this is pi. This angle right here is 3 pi over 2. And then this angle right here is both 2 pi and it's also 0. So what we recall for the sinusoidal functions is that they are cyclical. So if I do pi over 2 here, pi, 3 pi over 2, 2 pi, then I should see, let me zoom in a little bit, I should see a pattern repeating. So this is pi over 2, this is pi, this is 3 pi over 2, and then this is 2 pi. So when we get back to 2 pi, I have to be at 0. When I'm at pi, I'm actually at 0 too. But when I'm at pi over 2, I have a max of 1. That's this point here. And when I have 3 pi over 2, I have a max of -1. Or I have a local maximum or local minimum. So the sine is a wiggle that goes like this through these points, and it just keeps doing that forever and ever. You could ask what happens with the negative, negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. So this is negative 2 pi, negative 3 pi over 2, negative pi over 2. So remember, negative pi over 2 would again be negative 1. Pi is going to be 0, and then minus 3 pi over 2 is going to be positive 1, and that's going to be 0. So this function here wiggles like this before it got to that point there. So, and it just keeps going. So that's the sine. The cool thing to remember, or the important thing to remember, is the sine of 0 is 0. Okay, so that was actually, I made some Microsoft Excel. I did a quick plot of some of these solutions. So when you're talking about positive slope and intercept of 0, I made a table here. So for -2, -1, and 0, when m equals 1, you have this plot here. So for -2 in x, you're -2 in y. And then notice that when you are slope equals 2, you're a little bit steeper line, and when slope equals 3, you're even steeper still. So those are all positive slopes, and those are y-intercept is 0. Now for question B, these are all negative slopes. These all actually have the same y-intercept of 1, but I can change that here, change my y-intercept to 2. They go through the point at 2, change it to 3, and etc. 0.5. Those are all positive y-intercepts, and those are all lines with negative slope that go through that point on the y-axis. That is your y-intercept, and it's positive y-intercept. These are all going to be negative y-intercepts. If a negative y-intercept, it would look like this. They would be going through below the point 0, 0 on the y-axis. So what I like about Excel is that you can kind of change stuff here, and if you've done your formulas right in Excel, they show up pretty accurately.